In this video series, we will cover SN1 reactions. Now, keep in mind that if you find that these videos move too slowly, you could just try the problems in the problems document, check your answers against the answers document, and skip to the parts of the videos that cover problems that you find to be difficult. Now, this video series on SN1 reactions is going to build on the ideas we introduced in my previous series on SN2 reactions. In this first video, we're going to cover some fundamental concepts and techniques that apply to Ochem reactions in general. And then starting with the next, second video in this series, we will apply those fundamentals to understand specific SN1 reactions. Well, let's begin by reviewing some ideas that we did introduce in the SN2 series. I'm going to be asking you a series of questions here, and I hope that after each question you will pause the video and come up with your own answer. I'm going to go through these questions pretty quickly because I did cover them in more detail in the SN2 series. Question: what is the most important factor in organic chemistry? Answer: formal charges. Question: what is the most important tool for predicting what will happen in a reaction? Answer: formal charges. Question: when you draw the products of a mechanism step, what is the most important part of the products to get right? Again, I hope that you're answering each of these questions on your own. Answer: formal charges. Question: does nature like or dislike charges? Answer: we can pretend that nature is a person and pretend that nature dislikes charges. That will help us to get better intuition for the reactions. Question: does nature prefer atoms to be charged or neutral? Answer: nature prefers neutral. Question: does nature prefer large or small formal charges? Answer: small formal charges. Question: which atoms are most likely to participate in a reaction? Answer: usually the atoms with formal charges are most likely to participate in a reaction. Why? Because nature dislikes formal charges. If nature sees an atom with a formal charge, nature is going to dislike that it has that charge, and nature is going to want that atom to participate in the reaction so that the atom can get back to neutral. Now, there is an important exception to this pattern. A metal with a positive formal charge, such as sodium plus or potassium plus, is usually a spectator ion which does not participate in the reaction. We talked about all of these ideas in more detail in the SN2 series, and we will be illustrating what these ideas mean and how these ideas are useful, again, in this series on SN1 reactions. But now would be a good time to pause the video and make sure that you have memorized all these key ideas. And then in the course of this SN1 series, we'll show why these ideas are important. Now, we've seen that the most important tool for predicting what will happen in a reaction is the formal charges. That means that the most important tool for drawing electron-pushing arrows is formal charges. So now let's review how we can use the formal charges to draw the correct electron-pushing arrows. Please pause the video and try this problem. Show what formal charges we would place at the beginning, middle, and end of a series of electron-pushing arrows. And your choices are positive, negative, and neutral formal charges. I hope you gave that a shot. Here's the answer. Was this your answer? Remember that these arrows show the movement of electrons. And remember that electrons have a negative charge. Well, it should make sense to you that we'd like to put a negative charge at the beginning of the series of arrows because negative electrons would like to move away from a negative charge. And it should make sense that we would like to put a positive charge at the end of the series of arrows because negative electrons would like to move towards a positive charge. Now, you can't always put a negative at the beginning and a positive at the end, so it's okay as well sometimes to put a neutral atom at the beginning or end of the series of arrows. We would almost never put a positive charge at the beginning, and we would almost never put a negative charge at the end of the series of arrows. I hope you can see why that would not make sense. For example, if you put a negative formal charge at the end of the series of arrows, then electrons would be moving towards that negative charge and making the negative charge even bigger. But remember, nature doesn't want to make charges bigger. Nature wants to make charges smaller. We should almost always put a neutral atom in the middle of the series of arrows. We almost never put positive or negative atoms in the middle of the series of arrows. Remember here that we're talking about formal charges. We are not talking about delta charges right now. That's a separate system. Now notice that here we showed a series of 2 electron-pushing arrows. Many mechanisms involve a series of 2 electron-pushing arrows. However, in this video series on SN1, we will also see many mechanism steps that involve only 1 electron-pushing arrow. So let's try this exercise. Please pause the video and show the formal charges that we would place at the beginning and end of this single electron-pushing arrow. If this was the only electron-pushing arrow in a mechanism step, what formal charges would likely go at either end of this arrow? Here's the answer. Well, again, we would usually want to put a negative formal charge at the beginning of the series of arrows and a positive formal charge at the end of the series of arrows. Or if we can't do that, we would put something neutral at the beginning or something neutral at the end. We would almost never want to put something positive at the beginning of this arrow, because if something is positive and negative electrons move away from it, it would become even more positive. Well, nature doesn't want to make something positive even more positive. So at the beginning of this arrow, we should put something negative or neutral, almost never positive. At the end of this arrow, we should put something positive or neutral, almost never negative. So this is how we would handle a mechanism step that involved only 1 electron-pushing arrow. We'll get some practice with that in this video series. By the way, notice that in this first example, I drew the negative charge on the left and the positive on the right. And here I drew the negative on the right and the positive on the left. But hopefully that doesn't seem like a contradiction. Left and right is not what matters. What matters is where the electron-pushing arrows begin and where they point to. In this case, the electron-pushing arrows were pointing from left to right. And in this case, the electron-pushing arrows were pointing from right to left. In both cases, we'd like to put a negative formal charge where the arrows begin and a positive formal charge where the arrows end. In that SN2 series, we covered 3 roles that atoms can play in organic chemistry reactions. What are 3 important roles that atoms can play in reactions? The 3 crucial roles are nucleophile, electrophile, and leaving group. How would you define the term nucleophile? Here's a good definition. A nucleophile donates electrons to join an electrophile. Notice that that's a 2-part definition. How would you define electrophile? Again, I hope that you're pausing the video after each question and coming up with your own answer. An electrophile receives electrons to join a nucleophile. Again, that's a 2-part definition. How would you define the term leaving group? A leaving group receives electrons to leave an atom. Again, that's a 2-part definition. These definitions are fundamental to organic chemistry. You need to have complete mastery of these ideas. Now, the reason we identify these roles is so that we can draw electron-pushing arrows. So next question, how would you draw the electron-pushing arrows for a nucleophile, for an electrophile, and for a leaving group? How would you draw the electron-pushing arrows for these roles? Well, remember that electron-pushing arrows show the movement of electrons. So we should draw this arrow to show that the electrons would move away from a nucleophile and towards an electrophile. A leaving group also receives electrons, so the electron-pushing arrow should point towards the leaving group, away from the bond, which is going to break when the leaving group leaves a specific atom. Keep in mind that the atom that the leaving group leaves might be part of a larger molecular structure. Usually the atom that we leave will be part of a larger molecular structure, like this. We can use these terms for the head and the tail of an electron-pushing arrow. A nucleophile goes at the tail of the electron-pushing arrow because it's an electron donor. An electrophile and a leaving group go at the heads of electron-pushing arrows because they are electron receivers. Now, how can you tell what role an atom will play in a reaction? In our SN2 series, we covered some important clues for each of these roles. What's an important clue that you can use to identify when an atom is likely to play the role of nucleophile? Answer: atoms with negative formal charges are likely to play the role of nucleophile. That makes sense because if something has a negative charge, it would like to get rid of that negative charge by donating its negative electrons. What's an important clue for when an atom can play the role of electrophile? The clue we discussed in the SN2 series is an atom with a delta positive charge is likely to play the role of electrophile. That makes sense because if something has a positive charge, it's going to tend to attract negative electrons. A positive charge would attract negative electrons. What's a good clue to help identify when an atom can act like a leaving group? In our SN2 series, we memorized that neutral chlorine, bromine, and iodide are good leaving groups. And we also learned that another functional group called sulfonates are also good leaving groups. And we learned that other neutral atoms besides these are usually not acceptable leaving groups. We'll get a chance to review sulfonates further later in this video series as well. All the material that we have on the screen right now is material that we covered in that previous video series on SN2 reactions. Well, we know that if we see a negative formal charge, that's a clue that an atom can be a nucleophile. But what if none of the starting materials has a negative formal charge? If none of the starting materials has a negative formal charge, how do you find the nucleophile? You would need another clue. So here's another clue you can use for nucleophiles when nothing has a negative formal charge. Well, here's the clue. If there's no negative formal charge, you can also use a neutral atom as the nucleophile if the neutral atom has a lone pair. Remember that a nucleophile is something that will donate electrons, while a neutral atom can donate its lone pair. A lone pair is not as stable, not as happy as electrons in a bond. So when there are electrons in a lone pair, they would like to be donated so that they can move from a lone pair into a bond. That's an explanation for why a neutral atom with a lone pair wants to be an electron donor, wants to be a nucleophile. All right, now in practice, this is almost always going to apply to one of these four atoms: neutral oxygen, neutral nitrogen, neutral sulfur, and neutral phosphorus. Neutral oxygen, nitrogen, sulfur, and phosphorus all have lone pairs. So these are all elements that you could use as nucleophiles even when they're neutral. Can you find those elements in the periodic table? The elements we were discussing are these four. These four: neutral nitrogen, neutral oxygen, neutral phosphorus, and neutral sulfur. So you should have memorized that when these elements are neutral, they have lone pairs. You should have memorized that when these elements are neutral, they have lone pairs, which makes them candidates for neutral nucleophiles. Now, unfortunately, almost every rule in organic chemistry has an exception. So there is an exception to this rule. There are some neutral atoms with lone pairs that are not nucleophiles. The exception is neutral chlorine, bromine, and iodide. Neutral chlorine, bromine, and iodide do have lone pairs. These have lone pairs, but they're usually not nucleophilic. you can see that chlorine, bromine, and iodine are not on this list of the neutral nucleophiles. This shouldn't be too surprising to us because we've already learned a different role for chlorine, bromine, and iodide. We've learned that neutral chlorine, bromine, and iodide are good leaving groups. So it shouldn't be surprising that neutral chlorine, bromine, and iodine will not usually be nucleophiles. For the most part, usually we will not use neutral chlorine, bromine, and iodine as nucleophiles. Here's neutral chlorine, bromine, and iodide in our periodic table, and we usually will not use neutral chlorine, bromine, and iodide as nucleophiles. Now we would use negative chlorine, bromine, and iodide. These are all excellent nucleophiles. These are all excellent nucleophiles. Negative chlorine, negative bromine, negative iodide, those are all good nucleophiles. But neutral versions of chlorine, bromine, and iodine are not nucleophiles, even though they have lone pairs. These do have lone pairs, but they're still not nucleophiles. This is a good example of how the most important factor in organic chemistry is the formal charges. You can't just say chlorine is a good nucleophile or chlorine is not a good nucleophile. You have to specify the charge. You have to say negative chlorine is a good nucleophile and neutral chlorine is usually not nucleophilic. It's not enough to focus on the element, you also have to focus on its formal charge. So again, these are the elements that we can use as nucleophiles even when they're neutral. These are the neutral nucleophiles circled in red. To review, how do you identify a nucleophile? Well, first, look for an atom with a negative formal charge. But if you don't see any negative formal charges, next look for a neutral atom with a lone pair. That basically means neutral oxygen, nitrogen, sulfur, or phosphorus. But keep in mind that we do not use neutral chlorine, bromine, and iodide as nucleophiles, even though they have lone pairs. Those are leaving groups. By the way, if you have a choice, who is probably going to be more nucleophilic? An atom with a negative formal charge or a neutral atom with a lone pair? Well, usually the atom with a negative formal charge will be more nucleophilic. Remember, the most important factor in organic chemistry is the formal charges. So if there's an atom with a negative formal charge, you should usually prefer to use that as a nucleophile instead of a neutral atom with a lone pair. We usually only use a neutral atom with a lone pair as a nucleophile when there are no atoms with negative formal charges. There are some exceptions to what I just said that you'll have to learn later in the course. So we've seen that if you see a negative formal charge, you can guess that that can be a nucleophile. But what about if you see a positive formal charge? Well, it turns out that when you see a positive formal charge, the role depends on the identity of the atom. For example, if you see a carbon with a positive formal charge, that can be a good electrophile. When a carbon has a positive formal charge, the carbon can be an electrophile, and that will play a crucial role in all of our SN1 mechanisms. So let me repeat that. When a carbon has a positive formal charge, the carbon can be an electrophile. That will play a crucial role in all of our SN1 mechanisms. Pause the video and explain to yourself why it is reasonable that a positive formal charge could make a carbon electrophilic. Well, I hope you used this definition. A positive formal charge would make you want to receive electrons. Remember that electrons have a negative charge. Positive charges attract negative charges. So this clue makes good sense. If you have a positive formal charge, it does make good sense that that would make a carbon more eager to receive negative electrons. A negative formal charge makes an atom eager to donate electrons, and it makes sense that a positive formal charge makes an atom eager to receive electrons. We know that an atom with a delta positive could also be an electrophile, but if you see a carbon with a positive formal charge, that will generally be a better electrophile than an atom with a delta positive. So if you see a carbon with a positive formal charge, don't bother looking for anything with a delta positive. You can just use the carbon with the positive formal charge as your electrophile. Now, what about if there is a positive formal charge on an atom that is not a carbon? Well, earlier in this video, we mentioned that when you see a positive formal charge on a metal, such as sodium plus or potassium plus, that will usually be an unreactive spectator ion. Metals with positive formal charges, such as sodium plus, usually don't participate in the reaction. Obviously, there are other situations with a positive formal charge besides these two, but we don't need to discuss those at present. Later in this video series, we will see another type of role that an atom with a positive formal charge can play, but this is all that we need to discuss about positive formal charges for the time being. So the material on the screen now summarizes some crucial information that we will be relying on repeatedly during this SN1 series. So you need to make sure you have mastery of this material on the screen. Now, I know that actually the material on the screen here is starting to get a little bit complicated, isn't it? But there's not much we can do about that. That's why organic chemistry is a difficult class. Organic chemistry is a difficult class because the information you need to learn can get somewhat complicated. So this material is getting a little complicated, but you do need to have mastery of these ideas to succeed in your Ochem studies. And in particular, you need to have mastery of this material to succeed with SN1 reactions. Now would be a good time to pause the video and, first of all, make sure that you have all of this information clearly recorded in your notes. And secondly, make sure that you've made an effort to memorize this key information. Okay? I hope that you made an effort to do that. Well, of course, all of these ideas will start to become clearer and make more sense once we start applying them to actual SN1 reactions. And we'll start doing that in the next video, the second video in this SN1 series.